Section 7.5 is about formulas and variation, and what these are basic equations that scientists use to either understand a situation mathematically or to take an existing equation and rearrange it to make it useful for something different. The first topic, the one that's a little bit more algebraic, is the one called formulas. The idea here is to take an existing formula and rearrange it to solve for one of the letters that's not currently isolated in the equation. And the best way to approach this is to start by asking yourself the question, what would I do if the letters were numbers? So, look at this equation. The letter you're trying to solve for is A. What if everything else in the equation was a number? So instead of r equals ab over a plus b, you might have 37 equals a times 5 over a plus 5. And ask yourself what you would do there. This will be just normal algebra like you've used back in Algebra 1, and it'll tell you what you're going to have to do with the letters. So here, the first thing you would probably do, I expect, is you'd probably multiply the denominator up to the other side. Well, in the actual problem we're doing, let's do the same thing. Let's multiply the denominator up to the other side. Okay, let's see, what would we do next? Well, we would probably distribute this 37 in. And one of the tricks to doing this the most efficient possible way is try not to do any of the arithmetic. Like, don't grab a calculator or a piece of paper and pencil or do it in your head. Don't try to figure out what 37 times 5 is. Just leave it 37 times 5. That might seem a little lazy, but it actually helps over here with the letters, because with the letters, you can't work out what r times b is. You have to leave it as r times b. So if you want the numbers to lead you to what you have to do with the letters, it's actually better if you don't do the arithmetic. Just leave the arithmetic undone. So then, maybe the next thing you would do is get the a's on one side. And I know you're probably thinking subtract 5a from both sides, but realize, with the letters, you don't really know which one is bigger. So if you didn't know which one is bigger, it probably would seem more sensible to subtract the 37a on both sides. So then you'd have 37 times 5 equals, and again, don't do the arithmetic. It's 5 minus 37. Don't work out what that is. You would do the same thing over here. You would subtract RA on both sides, and you would have RB equals, and here you would have B minus R times A. There, you can't do the arithmetic. So with the numbers, don't do the arithmetic. It'll be a better guide for what to do with the letters. And then to solve for A, your last step would be to divide by whatever coefficient A has, and you would make, a fraction that would look like this. Well, we do the exact same thing with the letters. Divide by the stuff in parentheses, that's the coefficient of A. So we're going to divide by B minus R, and that's our answer. So once you get used to this, and you've worked these problems plenty of times, this stuff over here on the left will be optional. You don't really have to do it. I'm not going to grade you on your test based on whether you did that stuff or not. But it's a really good tool when you're not sure what to do. If you're looking at a problem brand new and you're not quite understanding how to get started, that's what you can do to figure out what to get started. This is how you're going to handle the first half of section 7.5, the part of the section that has to do with formulas. The second part of the section has to do with a topic called variation. And what this has to do with is building equations based on relationships that you can kind of get from common sense and life experience. The two types that we're going to care about in this class are direct variation and inverse variation. So with direct variation, the idea is that as one of the quantities gets larger, the other one will get larger. So a sentence that you could imagine sort of just deriving from daily life and experience is you might decide that the stopping distance for a car, oops, forgot the letter N, I can spell. The stopping distance for a car, that gets larger and larger and larger the faster the car gets. So you could say that the stopping distance varies directly as the speed of the car. So you could translate that sentence, that vague idea that faster cars are harder to stop and slower cars can stop quicker. You can take that basic idea and turn it into sort of the beginning of an equation. And the equation that you would turn it into is something equals k times the other thing. Typically what we suggest that you do is use letters of the alphabet that are easy to remember. Don't try to write everything as y equals k times x, because you don't know what y stands for. You won't know what x stands for. So instead of using y and x all the time, we suggest you use letters of the alphabet that sort of automatically make sense, like D for distance and S for speed or something like that. Maybe R for rate, something like that. You get a similar kind of equation for situations in which the two quantities you're talking about, they sort of go in opposite directions. Like, for example, a sentence that you could imagine from just daily life is how long it takes to pack varies inversely with the number of people you've got helping. Like, imagine, you're moving from one apartment to another. And you've got like all your friends helping you. That job goes a lot faster than it would if you didn't have all those friends. If you're just doing it by yourself, it would take a really long time. If you've got a whole bunch of friends helping you, it's going to go very quickly. So the length of time is shorter with more people. So you increase the number of people, you decrease the length of time. And vice versa. If you have fewer people, the length of time is going to get larger. So that's a type of relationship we call an inverse relationship. And the equation you get there has to do with division. So the length of time to pack varies inversely as the number of people. That's going to be a division problem. In both of these cases, you have some sort of unknown extra variable, and that thing is called the constant of variation. And it definitely varies from problem to problem. Like, for example, if you were packing up a little tiny apartment, then the relationship between time and number of people, that's not going to be the same relationship as if you have a giant house with 3,000 square feet worth of stuff. So the quantity for K is going to vary from situation to situation, but still you'll have the same basic relationship that more people will make it take less time. Same thing with the stopping distance for the car. If the road is really slick, the total distance is going to be more, but it'll still be dependent on the speed. More speed will still add up to a longer distance. Now, I mentioned at the beginning of this that there are two types of variation we care about, direct variation and inverse variation. But there actually is a third type, sort of. The third type is called joint variation, where they say something varies jointly as something and something. All that really is a combination of the other types. So if you were to say that the packing varies directly, so packing time varies directly as the square feet, and inversely as the number of people, that's joint variation. That's variation where you've got more than one type of variation happening at once. And in that type of situation, you can get an equation that looks like this, where you're multiplying by the square feet, but you're dividing by the number of people. That type of multiple different relationship situation is called joint variation. So really there's only two types, but you can also combine the two types and make a combination thing. The real tricky part of variation problems is how you actually work through the sorts of problems that you're actually asked. So let's look at an actual example. This example here is a pretty standard type of a problem that you run into when you're doing variation. And there are really three main steps to these sorts of problems. The first step of a problem like this is to translate from words into some sort of basic equation. So the words here that we have at the beginning of the problem, the very first sentence, and I guess I should warn you, it's not always the first sentence. It's not like the English language is that simple and easy to understand. But in this case, it's the first sentence. You read the sentence that is telling you the general relationship between the quantities. So here, this talks about variation. See the word varies right there. It says directly. And the things that are varying are signal strength. So I'll just use S to stand for signal strength. And it's varying directly, so it's going to be K times something. And it's directly as the power. So power. There's my equation. Oh wait, there's more. And inversely, okay, inversely means we're going to divide. Inversely as the square of the distance. So I'm going to take distance squared. And you can do that. If they say like the square root of the distance, you would put square root of the distance in there. If they were to say the logarithm of the distance, you would put logarithm of the distance there. Whatever extra words they throw on, you just write that up as part of your equation. Don't let it distract you. Just keep going. Now, the problem with this equation is it's too general. This relates to all different possible signal strength relationships for all different transmitters and all different sorts of circumstances. It's too general. So the second step that you have to do is you have to sort of like narrow it down. You have to make it apply to this situation. And what that really boils down to is figuring out what that K thing is, that constant of variation. So step 2 is figure out what K is. And the way you do that is you plug in for all the other letters. Of course, that's only possible if somewhere in the paragraph they give you enough information. So you read through the paragraph, and somewhere in the paragraph they should tell you what happens with a particular power and a particular distance and what signal strength you end up getting out of that. So here, that turns out to be our second sentence. It says a power of 400 watts gives a signal of 40 RSSI, whatever that stands for, strength, at a distance of 30 feet. So that's going to allow you to plug in for power, for strength, for distance, and once you plugged in for S and P and D, K is the only letter left. So, plugging into this equation, here's all the stuff that we had before. Let's plug in for S. Okay, well S, that's signal strength. Make sure you don't just assume it's the first number. It's not. Signal strength is actually 40. Okay, then we plug in for power. So power isn't 30. Power is 400. Plug in for the distance. The distance is 30. So you plug in for all these elements of the equation, and now it's just a regular everyday equation, something like you would have seen back in Algebra 1. And you solve it. So let's see, where would you begin? Well, 30 squared, you'd probably do that first. 30 squared is 900. And you might reduce the fraction because, well, why not? So then you'd have 40 equals 4/9 K. And if you don't like fractions, you might multiply the 9 up to the other side, and then divide by the 4, and you figured out what k is. And then, once you've figured out what k is, you essentially combine step 1 and step 2 to create step 3. So for step 3, you actually answer the question. And the way you do this is you take the sort of super generic equation we started with, combine it with the k we just figured out, and finally read the actual question part of the question and see what you need to do. So here the question was, what's the signal strength if power is reduced to 300 and distance is reduced to 20? So take this equation, plug in power, plug in distance. The power was, I'm sorry, I have to scroll up and down for this. The power was reduced to 300, okay. So we got 300 there, and the distance was 20. So we plug in a 20 there. And then you compute that out, and you get S is 67.5. But there's one last little thing you got to be cautious about with these variation problems. The answers you get are always meaningful. They always stand for something real. And 67.5 is kind of a meaningless number. I don't know what that 67.5 means. Is that like $67.50? Is it 67.5 pounds? You know, what is that 67.5? So what you have to do is you got to go back and read the paragraph one more time and figure out what were the units of measurement for signal strength. So back up here, if you read this, signal strength was some weird unit of measurement I've never heard of before, RSSI. But luckily, you don't need to know what it means. You just need to copy it down. So the 67.5, that's 67.5 RSSI, whatever that means. And that's the final answer you get to that. So with these variation problems, first you have to memorize what direct and inverse mean. But once you know what direct and inverse mean, then you need to practice problems like this so you get used to these 3 steps. First you translate using what the word direct and what the word inverse, what they actually mean. Then you plug in for all the variables except k and figure out what k is. And then you answer the equation by using the general form with the k plugged into it. That's how you do variation problems.